All right, so now we're looking at our less electrophilic carbonyl derivatives. So that's our acids, amides, and esters. And the first reducing agent that we talked about with ketones and aldehydes was sodium borohydride. So we're going to look at that with these. And again, these are less electrophilic carbonyls. And what I want you guys to try and remember now is, was sodium borohydride our strong reducing agent or our weak reducing agent? Was it mild or was it really strong? So take a minute to think about that. Make your selection. Paused. You just restarted. Sodium borohydride was the more mild. This is our mild reducing agent. We mentioned that last time. The real importance of that last time was that we could essentially use these protic solvents like methanol when we were using sodium borohydride because it's not nucleophilic enough, it's not basic enough to just deprotonate the solvent. But it has greater implications than just that. It's not nucleophilic or basic enough to deprotonate our solvent. It turns out that when we have a less electrophilic carbonyl, it also can't even reduce that. So this is actually going to lead to no reaction. So essentially when we have a less reactive reductant and a less electrophilic carbonyl starting material, we get no reaction. And we have the blanks in there. Sodium borohydride is a mild reductant, It is too mild to reduce less electrophilic carbonyl derivatives. So that's just the situation with sodium borohydride. It's a really nice reagent. It's really easy to use. That's why people love using it for things like ketone and aldehyde reductions, but it is not possible to be used in this with these types of carbonyl derivatives. All right, and now we are talking about esters and amides. So sodium borohydride is not strong enough to reduce any of these less electrophilic carbonyl derivatives, but what we wrote about lithium aluminum hydride when we first learned about it was that it is a strong enough reducing reagent. It's super reactive, and it's reactive enough to reduce any polarized functional group. So this is certainly a polarized functional group, so we can use lithium aluminum hydride. Again, we have to use it with an aprotic solvent. So just because I've been writing diethyl ether a lot, I'll write tetrahydrofuran, so you could just write THF for that, but it's a cyclic ether. But essentially, this is just H-, right? It's a very reactive H-. So how is this reaction going to work? What's the mechanism going to be? Well, where is our H- going to add? It's going to be attracted to the most partially positive position, so that carbonyl carbon. So it would add in there. And whenever things add to carbonyls, the first step is always the CO pi bond breaking, because that's the weakest bond. We always break the weakest bond first. So that would mean that we have added our H on there, we have our OR, and we have O- as well. And this is what we often refer to as just our tetrahedral intermediate. Hedral intermediate. So any of these types of reactions where we have essentially with ketones and aldehydes, this isn't really an intermediate. This is almost the ending point. All we do if the ketone or an aldehyde is we then protonate to make the ending alcohol. But what did we just learn about with an equilibrium that we said was about 50-50? Essentially, this is a species that this pi bond also is able to come down and kick out this this alcohol is essentially a leaving group. That would generate essentially an aldehyde. So all of these pieces are still on there as the aldehyde plus OR-. And this is certainly an equilibrium arrow. In fact, the equilibrium might be a little bit to this side or a little bit to that side, but it really doesn't matter that much which side it is on. Why doesn't it matter? Well, we have an aldehyde now. And what's more reactive, an aldehyde or an ester? Yeah, we just talked a lot about how the esters, amides, acids are less electrophilic than the ketones and aldehydes. So essentially, lithium aluminum hydride, it has 4 H's on each aluminum. So we have a lot of H minus around. And H minus is going to react with this aldehyde even faster than it would react with the starting material. So while if this is intercepted by the OR, it would go back here, but then it's just going to go back because this is an active equilibrium. And when it bumps into an equivalent of H minus, that's kind of the end point here, right? Because when that happens, we form a strong CH bond. So we have that one and this one now, and we're kind of at an end point. There's no, if we wanted to move these electrons down, we'd either have to break a carbon-carbon bond or a carbon-hydrogen bond. And we know that those are stronger bonds. We know that if we're going to compare H minus or C minus as an anion compared to O minus is a much more stable anion. So this is a pretty unidirectional arrow, where this one was an equilibrium arrow. So we're almost at an endpoint. This is an endpoint where we're not going backwards anymore, but the last thing we're doing is trying to isolate this sample. And remember, we need things to be neutral when we isolate them. So the last thing is we're just adding some H3O plus to this. That's going to lead to just an acid-base transfer to give us our alcohol product. So that's how that works with lithium aluminum hydride. It always leads to full reduction. So yeah, we can even write that down. LAH, lithium aluminum hydride, always leads to full reductions of polarized functional groups. So this is a polarized functional group. We got a full reduction. And what I have at the bottom of the page as well is that LAH reduces carboxylic acids and esters to primary alcohols. This is a primary alcohol. So whether we're starting with an ester or a carboxylic acid, it's going to work with both the same way. We're going to get primary alcohols from that. Yeah, so next we're moving on to amides. All right, so what about amides? So amides can also be reduced with lithium aluminum hydride. We already said it reduces all polarized functional groups. So we have our amide, we have lithium aluminum hydride. We're going to use our A product THF as our solvent. And how is this reaction going to work? Well, we have H minus, and again we said H minus with lithium aluminum hydride is really nucleophilic and basic. And it turns out that in this case, it's actually going to be deprotonating this nitrogen instead of adding directly to that carbonyl carbon. So that would actually be the first step, is just deprotonating that hydrogen. So how does it work then? How do we get the reduction of the amides, or actually the carboxylic acids too, because that OH bond would also be deprotonated by that hydride. But essentially what happens in both of these cases is that instead of having OC or OH as our leaving group, I'm just going to draw a couple arrows to show this, but essentially we're going to have an O aluminum leaving group. It forms a pretty strong bond, and essentially at this point, and this full mechanism is in your textbook, so I would recommend, if you're interested, to check that out. But for both carboxylic acids and amides, this is going to be the leaving group. We're going to form some intermediate with a C double bond N. By deprotonation of that, this nitrogen-hydrogen bond, the electrons in that would be forming the pi bond there, and then the pi bond here would come up to make the aluminum bond. But then at that point, this hydride can add in, form a tetrahedral intermediate that's pretty unstable if we think about it. Nitrogen does not really like to be negatively charged. And then at that point, those electrons can come down and kick out the OAlH2 intermediate. At that point, we again have a pi bond, and we still have H minus around, and that H minus can then again add to there to form the two hydrogens on there, the NH minus, which will form a bond to the aluminum as well. So essentially we will have this bonded to the aluminum. So we can draw another one there. AlH3, draw a bond to that. That would produce this intermediate, and then essentially when we add our second step, when we add our H3O plus and water, the water is going to be adding to that aluminum. It's going to break up that bond, and the nitrogen will then protonate from the H3O plus to generate an amine, so an NH2. So reducing a carboxylic acid or an ester with lithium aluminum hydride leads to the primary alcohol, but reducing an amide with this lithium aluminum hydride reagent generates an amine. And I have that as the bullet point at the bottom. LAH reduces amides to amines. So that's how it works with these. Essentially we see that reduction of these less electrophilic carbonyl derivatives. You can essentially make an alcohol if you have just oxygens as part of that functional group. But once you have the nitrogen as part of that functional group, you will get the amine out instead of the alcohol. So we've talked about sodium borohydride. It's not reactive enough to reduce any of them. Lithium aluminum hydride fully reduces them. So what if we wanted to go from like an ester to an aldehyde? How would we do something like that? Turns out that there is a special reducing reagent that does that as well, and we're going to talk about that next.